Graph, we have several critical points. Okay, we have maximums, minimums, and zeros. You should know what zeros are. Tell me what zeros are. What intercepts? Close. Try again. X. Zeros are x-intercepts where it crosses the x-axis. We did that a lot with our quadratics, right? Yes, and our PRZs. We've talked a lot about zeros as functions. Maximums and minimums. So we talked about this a little bit with parabolas, but it impacts the range, yes, the maximums and the minimums. But what if I have something like this, which looks like what kind of function? Quartic. Yes, a quartic. This has several maxes and mins, or actually a couple of maxes and one min. If you look where it's topping out here, okay, sometimes we call these turning points. Because if you look, it starts going up, 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 up. Suddenly it stops going up, it changes direction and starts going down. That's the point where the maximum occurs, okay? So it's the highest point right there. But if you notice, if you look over here, there's another one, right? So it can have more than one max or min, okay? But there's two different kinds. There's what we call absolute and relative. So absolute, and this applies to maxes and mins. Absolute is the absolute highest or lowest point on the graph. No other point goes higher or lower than that one. So I always say the high or low point, okay, if it's a minimum. Whereas relative, it's a turning point. It changes direction, but there's a point that may be higher somewhere, okay? So relative is a high or low in an area of the graph. Sometimes they're called local max or min, because locally, right there, right around where it is, it's a high point. But if you look at the graph as a whole, it's not the highest or lowest. So looking at this first maximum, would you say that that is a relative or an absolute? Relative. And the reason being there's a higher point, which is here. Would that be relative or absolute? Absolute. Do you see any mins? Yes. So it looks almost like the vertex on it. Yeah. Area. Yeah. It's almost like the vertex of a parabola, okay? In fact, it is the vertex of a parabola if I'm talking about a parabola. Would that be relative or absolute? It's relative because there are lower points on this graph than just this one. The graph goes down forever, okay? Now, do not do this. Do not get on your graph and go, oh, look, I found a minimum. It's the arrow. No. The arrow indicates that it goes down forever. It's not actually a minimum point. Does that make sense to you? Do you understand the difference in relative and absolute? It's a fairly easy concept. It's finding them that gets difficult. Are we all okay? All right. Okay, so
absolute because what happens if that W is
that's exactly. Let's say that these are at the same height. You can't have more than one absolute, so they're both what? Relative. Let me show you one more. What's the graph? What do you think that might be? It's a cubic. What about critical points here? And we're talking max and mins, not zeros, because I don't have the axis on here. Why are they relative? Because this is a high point, but there are places on the graph that are higher. This is a low point, so it's relative, but there are places on the graph that go lower. So let's get to the hard part. Yeah.
So for the absolute maximum, we just say like the arrows.
No, it does not have to have any of them. Yeah, it doesn't have to have them. Before I show you how to find these actual points, let me talk about domain and range just a second. I know. Because I love y'all. I want you to have all this information.
Yeah, everybody's forgetting. They really need to stop using my math classes.
I'm going to give you the coordinates of this point just for the sake of example here. All right. Yes, y'all are right. That is a quartic. And so on this quartic, I could talk about, well, we could do the end behavior as it sits. What do the ends look like? As x approaches positive, what does y do? Positive. As x approaches negative, y approaches positive, right? It's positive both ways. Now, when I start talking about domain and range, and we have talked about domain and range extensively, right? And we've done it with parabolas. We've not really done it with all these other funky shapes. So let's look at it for just a second. The domain here, so I'm looking left to right. What is the domain of this function? Yes. The domain is negative infinity to positive infinity. All real numbers. There's nothing that you could not plug in for x. There's no point left to right that the graph would not be defined. Right? We all understand that? Range is the one that's restricted. And anytime you have an absolute max or min, your range is restricted. Okay? What is the range of this one? -2. Yes. It is a bracket because there is a point at -2, and then it goes up to infinity. Okay. You do like it? Good. All right, so as we look at domain and range, we have to know these critical points. So let's take out our calculator. And I think the easiest thing, because you have all the tools at your hand other than finding the coordinates of doing a full analysis.
Wait, is it possible in the range to have two positive numbers? Like if that graph was up to 1, 2, instead of 1, -2, would you still put the 2 and then?
So if it looked, what'd you say if this was 1, 2?
Yeah, if that was positive, it would still going up.
So it would be 2 infinity.
Yeah, I didn't know if you could have
Yeah.
two positive.
Oh yeah. Just make sure when you write it, you start with the smallest value up to the biggest. Yeah. I'm sorry.
For like
Is that the charger for it?
with the domain and range, would it be like negative
Say that one more time.
with the for the cubic?
Yes, negative infinity. Yep. That's a good question. So with a cubic graph, that's a terrible cubic graph. Let's make it go the other way. Maybe I can draw it better. Domain here, yes, is negative infinity to infinity. And the range as well, because any of your odd degreed functions are going to be negative infinity to infinity for both. Because the ends go, every odd degreed polynomial, the ends go opposite directions. The evens are the ones that are going to throw you. That's right. Stinking even functions. Yep.
When is it never?
Like if it has like two
Yeah. Or we will get to some, and we're not there yet, but we will get to some that have some that do like this. This is yeah. We'll get to some that have some restricted domains and some things like that, or some that have a starting point and go off. We'll get to all of those. We're just not there yet. We'll get to some restrictive domains. We just haven't yet. All right. I think the best thing to do is let's just jump in and do one together. If you would like to.
Can we do number 1 together?
Okay, we'll do number 1 together. Now, I have to, through this, I'm going to have to stop and show you how to calculate these points, okay? So y'all stay with me. All right, number 1. We have 1/8 times x plus 4 times x plus 2 times x minus 3. This is f of x. So before I can perform, now when you plug this in your calculator, I would advise you leaving it like this. Your calculator can take it, all right? But when you're finding your leading coefficient, your degree, your type, all those little first things, you're going to have to FOIL it out and multiply it out to find them, okay? But if you were to make a mistake on that in the algebra part of it, and then you plug that in your calculator, then you've also made a mistake on the graph, the critical points, the domain, the range, the zeros, everything, right? All right, so let's multiply it out. So the first two, since that's a fraction in the front, I'm going to leave that for the last, because, all right? So I have x squared, 2x and 4x gives me 6x plus 8. And then x minus 3. I'm not going to skip any steps when I do this one. X cubed minus 3x squared plus 6x squared minus 18x plus 8x minus 24. Remember, I still have this 1/8 that's sitting out here glaring at me. All right, let's get the like terms together. X to the third plus 3x squared minus 10x minus 24. Yucky, yucky, yucky. 1/8 x cubed plus 3/8 x squared. Remember, we're not going to really do anything else with this. We're not plugging any numbers in or anything, so the fact that it's kind of nasty is okay. 10 over 8x, or 5 over 4. 24 divided by 8 would be 3. So now looking at this, what is the type? Cubic. Do I need to give y'all a second to catch up with me? Okay. Y'all are supposed to... All right, so we said the type was cubic. The leading coefficient, 1/8. Don't keep the x on there. It's a coefficient. It doesn't have a variable. Constant, -3, which means the y-intercept is 0, -3. Did I miss anything? Degree. All right, we're ready to graph. Y'all ready? Oh, here we go. Buckle up. Okay.
Wait, is that
LC. Remember, same as the review. Remember, fractions need to go in parentheses. So I have x plus 4, x plus 2, and x minus 3.
There's no absolute fraction.
That's okay. Yeah, you would just write none.
Like, if it's just an error point, you have to do that. Wait, do you want to type it in?
What? The equation? Yeah, because I'm going to show you how to calculate, use your calculator to find the critical points. Because you need the coordinates of those critical points. Focus, Wills.
I was just writing the big there.
All right, I'm going to zoom 6. It's Valentine's Day.
Wait,
All right, so can you see all the critical points here that you need to see? Yes. I'm going to zoom in just a little bit on it because I know that I need to find all the zeros and all the maxes and mins. And if you look here, it's coming up, it's crossing, and it's coming back down. And so I just want to see that a little better. So I think I'm going to cut some of the top off and maybe a little bit at the bottom. So maybe my y's, I'll go from -5 to maybe 3. This isn't exactly necessary because you can see everything since it's a cubic, but just so I can, as I calculate these points, see how it's a little bit easier to see? I changed my y's, and I'm going to change my x's too, from maybe -5 to 5. I'm just kind of trying to get a really good picture here. So that whenever I calculate, I can really, you'll see why in just a minute, because I'm going to have to use some features of calculating. So one of the things I have to do is sketch it, right? And so I would use that graph to sketch onto the little graph given to you. Remember, you don't have to be exact by any means. Let's see, it's crossing at -3. So it's it's doing something like, I just want to get a,
It bottoms out at 1/4.
okay. Something about like that. It doesn't have to be exact. But what I'm going to do now is I'm going to use this picture to kind of identify my critical points, okay? So take out your calculator. We'll do the zeros first. Okay, how many zeros do you see on here? 3 of them, right? Now, it looks pretty clear that they're crossing at -3, -1, and +3. But we need to calculate those just in case. Somebody say wait? Okay. In fact, it's in factored form, so we know those are the zeros, but for the sake of example, we're going to calculate them anyway. If you hit second, is it easier for y'all if I do it from here instead of there so you can see what I'm pushing, or it doesn't matter? Okay. Second trace is calculated.
What?
Right next to graph, in between graph and zoom. Okay. Notice what we have. We have 0, min, and max. Okay, those are the critical points we're looking for. So choose 0 first. Now here is the part where students get confused. I don't understand why. It makes sense to me. All right, left bound. Okay, do you see my little spider that's blinking here? I'm going to use my arrows to control him. And I want to go to the left bound means get on the left side of the 0 that you're trying to find. Okay, so if I keep going left, Stay on. He's waiting on someone. All right. I'm still not there. That's pretty close to on it, but I need to make sure that I cross the axis to the left side. Now I'm clearly to the left of the 0. Do we agree? Hit enter.
Does it matter how far left you go?
Just don't go past another 0. Now it says right bound. What you're essentially doing is you're giving it a boundary and saying between these two values, find where it crosses the x-axis. Okay. All right, look, right bound, so go to the right of it and hit enter. Do you see these 2 arrows that are here? What it's saying is between these 2 x values, find one place between those 2 arrows where it crosses the x-axis. So do you want me to guess what's the work? Because that's what I wanted to do from the start. And it gives me that 0.
What did you say? Arrow home, down.
So there's my 0.
Wait, what?
Negative 4.
Shoot.
We knew.
You just want to be fast.
So on your graph, you would label a 0 at -4, 0. And then on your analysis paper, under the line that says zeros, and you don't have to actually put the coordinates here, you can just label it 0, and then the coordinates go on your line that says zeros. So one of the zeros is -4, 0. Okay?
So you want us literally writing Z
I literally want you to label, because you're going to label all the points on your graph and you're going to list the coordinates on the line. So this isn't necessary right here, but this and this are. Okay? Let's do the next 0. Again, second trace. Number 2. So now I'm talking about this 0, okay? So I want to be on the left side of it, but you don't want to cross over another 0. I tell students that are struggling with, I don't understand how far to go or what to do, put the spider as close to the actual 0 as you can, and then click left 3 times. Hit enter. Again, back to that point, and then right, 1, 2, 3. That's usually a good judge. 3 clicks will usually get you enough away from it to be good. Do you want me to guess? Well, that's why I did all this work. And so there's my next 0, which is -2.
I don't know what
That's crazy.
I'm just following.
All right, look at this
So
one,
wait, you
everybody
always
do
want
it.
to start on the right side of it?
It doesn't matter.
Well, why? Yeah, I think.
Now, when you do the boundaries, you have to be left side then right side. So when I do this 0, y'all watch my arrows this time. All right, I'm calculating this 0.
Oh, goodness.
Like I did.
my graph's on the way.
I think you hit trace and not calculate. And you kept scrolling on it. Alright, I'm going to do left bound and right bound, and I'm going to stop right here for just a second because I want you to see this. Alright, here are my 2 arrows. Here and here, when I do left bound and right bound. Essentially what it's doing is it's saying between these 2 boundaries, anywhere in here, does the graph ever cross? And if it does, that's what it's going to calculate. Your calculator just, you have to give it boundaries. You have to say, I want to find the 0 between these 2 values. That's all you're doing really. All right. And so this one is 3, 0. Okay. We're going to use the same technique with the maxes and mins. All right, so let's go back and calculate. Oops, see, I did it too. If you hit trace, that's not what you want. You want to make sure you call up second. See my little arrow that's telling me second? And then calculate, and we want this menu. All right. We'll do minimum next, since that's next on the list. Everybody agrees that this is my minimum, right? So I'm going to go to the minimum, but I need to go to the left of it. And this is where I think the boundaries make a little more sense. Because what it's going to do is it's going to find the lowest point between 2 points you tell it. So I say, okay, between here and here, what's the lowest point between those 2 points? Okay. Everybody make sure you can get that value when you put in your calculator.
Except for yours is a 4.
That's okay.
Mine's got
The
a
pixels
7.
and the calculator and the rounding and stuff, they're all. Yeah. Is that relative or absolute? Yeah. Relative, that's right. What'd you say, Kim? Make sure you get these values.
How many,
So do we write that number down?
So here I would say relative min. And then under your relative min list on your analysis sheet, you would put, round it off, maybe 2 decimal places, 1.08 negative 3.76. Okay, those are the coordinates of your relative min.
1. So you want 8, then we do max.
And then you do the max, and it's the same way. The process is the same for finding all of them. It's just you have to bound it. So y'all try the maximum real quick and see what you get, and then we'll make sure we all come back to the same thing. Yes. Go a little spider go. Yours is a lot faster than mine, I'm sure, because mine stalls out of here for some reason. Oh my gosh.
Good. Yeah. That's good.
Again, that's a relative max. Yeah. Thing. Are you domain and range on this one? The domain, yeah, this is an odd function, so it's negative infinity, infinity, and then the range is negative infinity to infinity. This thing is crawling because of this calculator. What? Because it goes, one end goes up and one end goes down forever and ever. Only even degree functions are going to have a restricted range. All right. Negative infinity to infinity on both of them. If you have something that you are multiplying together, and this is not the same one that's on the back of yours, but to find, I think one of the problems, actually I know one of the problems, it gives you dimensions of a box and it asks for the greatest volume possible. And this is the length times the width times the height, because that is how you find volume. If you were to graph this, it would be a cubic and would look something like this. For the maximum volume, you're looking for a maximum value, right? Doesn't that make sense? And so remember, this is in X and Y, and X is this value here, and Y would be your volume. So the maximum volume would occur when X is at this value, and that volume would be whatever that Y coordinate is, okay? So some of you had asked questions about, when will we ever use this? So I threw a few on there that you could see how we use these kind of functions to maximize and minimize things and find values to help with things like that. You're welcome.
So are we... Wait, so...